Okay, so today we're going to review a little bit from Friday before we actually start our resonance structure and formal charge lecture. The very first bullet here refers to C, N, O, and F should always follow the octet rule, which we know. B and BE, they're electron deficient, so B only needs 4 electrons to be full and 6 for boron. Second row elements never exceed the 8. We know that hydrogen only needs 2, right? Third row and heavier elements often satisfy the octet rule but can exceed the octet rule by using their empty valence d orbitals. So anything beyond 2, so 3, including 3, can expand the octet. And then when writing Lewis structures, specifically when looking at exceptions, if you remember something like this, we're going to put everything singly attached and counting the valence electrons. I need to know how many are available, how many total electrons are available. I'm going to bond everything singly first. Then I'm going to fill the periphery with my electron pairs, and any extra will go on the center. So I can have a maximum, like this has 12 electrons. 12 is my maximum of electrons for any expanded octet. All right, today we're going to be looking at resonance structures. If you remember, in some of the structures that we drew on Friday, we had bonds, multiple bonds, in needed, available, shared, that could be placed in our picture. So when you do needed, available, shared on this, you end up getting 8 electrons shared. So in this nitrate ion, and it's an ion, so we have the charge outside of these brackets, we have 4 bonds to share. Well, there's 3 oxygens, so that double bond can be placed in multiple locations. This can happen within the same molecule. I know they look like they're identical. However, the electrons within the same ion or same molecule can actually move around, making the existence of all 3. So an example of the movement, if I was going from structure 1 to structure 2, something like this would happen. This lone pair, a bonded pair, could move up here, and then we could get a pair of electrons moving there, making 1 become 2. If 2 were to become 3, we would have a lone pair moving here, and then a bonded pair moving up. You don't have to know how to do these arrows. I'm just showing you a little bit of organic chemistry so you can kind of learn something for next time. And then the reverse can happen. So that's why in resonance structures we have to have double-headed arrows in between each resonance structure, and that's actually a really important thing. So we're going to just practice again and draw some of these. CO2, you already pretty much knows what it looks like. You know what it looks like. So I'm just going to go ahead and draw all 3 resonance structures for CO2. So I have my triple bond and then my single bond, because remember this has 4 bonds in it. Because it's a resonance structure, I'm then going to place the double-headed arrows. And then my final one is single and triple. So there's all my electrons. It's super important when we calculate formal charge in a minute that we have every single valence electron in its place. So all the elements have to have everything filled up. So this one for needed, available, shared, since we don't know exactly what this one looks like, we need 24. 8 times 3 is 24. We have 6 plus 4 plus 5, and don't forget that little negative means we're adding a 1, so that is 16. Sharing 8. So again, we have 4 bonds in this picture as well. So like before, I'm going to draw my resonance structure with a double-headed arrow in between, and it's important to remember that this is a charged species, so I got to have the negative outside charged. And then I'm going to have 4 bonds, so I'll just do what I did before, a triple and a single resonance. Let's do double-double. And then we can do single-triple. All right, negative. So now I'm going to go place all these valence electrons because I have to. Make sure everything's filled up. So that looks like 1 electron. I want to make sure I see that's 2. That's important. Okay, again, make sure your valence electrons are visible. So these are the three resonance structures for OCN minus. One thing I want to point out is I want you to notice how these are equivalent. These are not equivalent structures. If you look back at the previous example, you see how all of these look alike? The only difference that we have is the location of this double bond, but the double bond is going to be same no matter where it's placed because it's an N double bonded to an O. So these structures are equivalent. So they're going to exist a third of the time. They're going to share how often those electrons reside between each oxygen. So the overall structure that we see is kind of an average of all of these. What's much different are these structures. If you notice, they're not equivalent. Here we have a triple bond and a single bond. In the first example, a triple and a single versus a double and a double. So they're not even equivalent. And these are really not equivalent because we have different bonds between different atoms. So how do we decide which one's the right one? In the previous, they're all the same, so they're all probably right. So they're all equal. But here we have an issue. The way you figure that out is calculating something called formal charge. Formal charge is an actual calculation you have to do for each atom. So for CO2, we have to calculate 3 formal charges, one for each atom, for 1C and for 2 O's. We use it to evaluate non-equivalent Lewis structures, so there's no need to do formal charge in that first example. Atoms in molecules try to achieve formal charges as close to 0 as possible. This is crucial, and I'm going to address that in a second. Any negative formal charges, if we have any, we have to be happy with that. We're better off if those negative formal charges exist on more electronegative elements. So how do we calculate formal charge? I really don't like this definition much, but it's the number of valence electrons from the periodic table. So you find your atom, you find its number of valence electrons, minus the number of valence electrons assigned to the atom in the molecule. In other words, you're going to take the lone electrons plus half of the bonded, because that one atom is responsible for only half of what's in a bond. It contributed one of those 2 electrons. So the best thing to do for us is just to go back and actually calculate formal charge for all of these. So again, I'm going to start here. It's the number, we're looking at oxygen. Oxygen has 6 valence electrons from the periodic table. From that, I'm going to subtract 1 for each electron and 1 for each of the bonded electrons, because there's 2 electrons in a bond. Half of 2 is 1. So all I'm going to do is go 1, 2, 3, 4, 5. I'm going to subtract 5. So this has a formal charge of +1. Carbon, valence is 4 minus 1, 2, 3, 4. Oxygen, valence of 6. Oh, so this is 0, sorry. Oxygen, valence of 6 minus 1, 2, 3, 4, 5, 6, 7. That's a formal charge of -1. Okay? So let's go on to the next one. These are not really useful unless we have other formal charges and compounds to compare. So we have to do it for all of the resonance structures. 6 minus 1, 2, 3, 4, 5, 6 is 0. 4 minus 1, 2, 3, 4 is 0. 6 minus 1, 2, 3, 4, 5, 6 is 0. 6 minus 1, 2, 3, 4, 5, 6 is 0. 4 minus 4 is 0. 6 minus 5 is +1. And I counted this one wrong. 6 minus 1, 2, 3, 4, 5, 6, 7. Bad teacher. It's -1. All right. So now looking at these, there's one that's obviously better than the others, and that would be this one. This resonance structure is the one that's going to exist the majority of the time because all its formal charges are 0. So why is a formal charge of 0 a good thing? Well, if you go back to the definition, whoa, I didn't want to go back that far. If you go to this definition, remember, formal charge is the valence electrons. Okay, so that's how many that the atom already has, minus what it has to share, or what it contributes. So isn't it the best scenario for an atom to contribute what it already has, right? So having a formal charge of 0 means just that. So 0 is going to be your most stable scenario. If you have a negative, what does it mean to be a negative formal charge? A negative formal charge means that the electron has a certain number, but it needs to share more. So it's going to have that extra electron, and it got it from somewhere, but it basically needs an extra electron and in order to become that charge. So what atoms are better off with extra electrons? Yes, electronegative atoms. So the more electronegative the atom, the better a negative formal charge works out. So let's do this now and apply to this next example. 6 minus 5 is 1. 4 minus 4 is 0. 5 minus 1, 2, 3, 4, 5, 6, 7. Woo. Yuck. Negative 2, no bueno. 6 minus 6 is 0. 6 minus 4 is 0. 5 minus 1 is negative 1. That looks a little better than the one on the left. 6 minus 1, 2, 3, 4, 5, 6, 7 is negative 1. 0, 1, 2, 3, 4, 5. And this would be 0. 5 minus 5 is 0. So this one's already out. Negative 2 is too far from 0. So that one is going to happen, but barely, like a couple percent of the mix. All right, because remember, a resonant is a mixture of all of these things. So looking at the next options, we have negative 1, 0, 0 in both of the cases. The question is, which one is it? Well, negative 1 means we need to share more electrons than we normally have, so we want to be a really electronegative element. Of the N and the O, which are the ones that are sporting the negative 1, O is the more electronegative. So this is the favored resonance structure. Another thing I want you to make note of, and if you haven't noticed it yet, the sum of all the formal charges, the sum of all the formal charges in the atom, or molecule, the sum of all the formal charges in the molecule is equal to the overall charge. So that's an internal check to make sure you do your formal charges correctly. Notice how all the formal charges in carbon dioxide add up to 0, because 0 is neutral. And look at all the formal charges of the next guy. Negative 2 plus 1 is negative 1, negative 1, and negative 1. So everything works out there. So that's about it. We will really quickly, I'll just do the formal charges on these and make sure, since this is a neutral atom, if we do the formal charges right, they should add up to 0. So each chlorine is 7 minus 1, 2, 3, 4, 5, 6, 7. So each chlorine has 0. Phosphorus is 5 minus 4, so that's a plus 1. And oxygen is 6 minus 7, and that's a negative 1. A negative 1 plus a plus 1 is 0. So those are the formal charges, and that is the assignment. So practice your homework.